There you can calculate probability. Essentially, it's a probability algorithm. You give the input, it tells output. But if somebody asks how it managed to go through, how that prisoner, even after so many large number of years, exactly the wall is intact, it went on the other side. How it did it, nobody knows. How is not answered, but the numbers are given. Right. But it just has probability, mod square probability. But how means in terms of what is the any classical trajectory or anything that we know. And probability means it gives the input or the conditions, it gives the chance that this will be. Just like playing a game of dice. It's a chance. It's like. So now that is all normal tunneling, which itself is so mysterious. Normal tunneling has so many aspects we don't understand. But client tunneling, I am coming to this picture. Sheet of graphene decorated with all type of impurities. And in client tunneling, what happens? This cartoon is shown. The probability is 100%. That means that prisoner, if it were a particle doing client tunneling, we could not care how thick the wall, the tall, the height. We could not care. I hope that is louder. Yeah. So it would not care how tall the barrier or high the barrier is. It will transmit with 100% probability. That is the very unusual property of graphene. Next slide. So here, just a schematic representation of the same idea. The electron comes to a barrier. What type of barrier? You can make a p-n junction. And it will not notice it. It will just run through. That is why the changes in the current I was showing that the RBC is crawling are very small, only 5%, 10%. Next one. And then a bit about the theoretical framework, how we can understand this unusual property, though I told the name client tunneling. As you may have studied some semiconductor physics. So there is a conduction band, valence band are there in semiconductors. In case of graphene, the band are linear in the momentum space, in case that is bit too high, don't worry. And then they meet at a point where there is no gap. So it's a zero gap semiconductor. That point is called the Dirac point. Next slide. Now the reason why this thing, does anybody have any book around? Oh, okay, great. Nice to know that this book is. Oh, that's even wonderful. It has a picture of Schrodinger's cat, dead or alive. It's a book on quantum mechanics by Griffith, I think. So, though it's a book on quantum mechanics, but you see it follows many classical laws. It's a book, right? Book is a classical object. So I can take this book, I can rotate it by 360 degree. What will happen? Same, right? I can rotate any number of times, it will keep coming back. 360 degree. It should come back, right? Okay. So then, but not all objects come back when they are rotated by 360. So can you think of any object which will not come back? Any object you are aware of? Triangle. Sorry, I don't have triangle around here, but even for triangle, if you rotate by 360 degree, it should come back. Rotate by 360, everything should come back. Right? Okay. I hope you are convinced about that. But if you take a pair of vectors on a sphere, this is a sphere, surface of a sphere. I have a pair of vectors like this. Then I go around, it's shown going around and coming back. That pair of vectors is not in the same orientation as it started. What we didn't really go 360 degree what it meant. We went around a loop and came back and it's not in the same place. But more interesting real world example is due to Dirac. So I will show this demo. This is a belt. Some rules are there. I am holding the two ends. And there is a problem. My hands cannot cross each other. So imagine that I had the hand but no arms. Imagine. Then how would I do it? I'll do it in that way. So this belt is also called Dirac bell trick. I'll rotate once, one time. I'll rotate another time. That's one time. How much rotation is there if I rotate it? Once. 180, right? 180 degree. Is that correct? 180 degree. I rotate one more time, it's 360 degree. Okay. Then I am trying to do this operation of going around. I am going this way. Now, imagine my arms were not there. So what I will do is just take it out and hold it in the same place. And you see, I could not bring it back. Once more, 360 degree rotation, 1 and 2. Now I am trying to bring it back to the old position. Just hold it, assuming that the arms are not there, and catch it here, and I could not. Now let me do it in a different way. I am turning once, twice, thrice, fourth time. How much of rotation is that? 720 degree. And then I am doing the same thing. Bring it here. It's back. Right? So once more, 180 degree, 360 degree, 540 degree, and 720 degree. There's 720 degree, and now I am doing this. I have to pass. My arms are preventing it. That's back. So you can see there are objects in the real world which come back to the old state with 720 degree rotation. But when you do 360 degree rotation, they don't come back. This is one example. It's not an object itself. The belt is a usual belt. If I rotate not a rigid body. It's an operation. The entire problem has been defined in a way. It's a mechanical analog, some sequence of steps which repeat after 720 degree but don't repeat after 360 degree. So that we say graphene's wave function is also like this. If you carry the wave function in the momentum space one time, it doesn't come back. You carry it 2 times, it comes back. That's an unusual topology. Next slide. I also always demonstrate this in my quantum mechanics course at IIT Madras. In fact, there is also a YouTube video I have uploaded on this. You can. My regular course. Something interesting you also record and put it on YouTube for all the courses I am teaching. Next slide. So this unusual property of the wave function, again I want to avoid too much of equation, so if it's familiar it's alright, otherwise there is a quantity called helicity, and in the hole and electron branch it takes certain value. Because of this unusual wave function, there is a quantity called helicity taking different value in the hole and electron branch. Next slide. That means if you make a transistor, NPN transistor, as you are familiar from your electronics or semiconductor courses, then the carrier which is electron here and in the P type it is a hole, it cannot get scattered because the helicity is parallel and anti-parallel to the momentum. Say here the momentum is in one direction. When it goes to the next branch, the momentum is, if the momentum goes in the opposite direction, the helicity is maintained. Helicity is parallel to the momentum in the electron branch, it is anti-parallel in the hole branch. So when it is moving from NPN and the helicity should remain constant, that means it should move like an electron and like a hole in the other side, in the barrier side, then again like an electron. So it will move as an electron, then suddenly move as a hole in the opposite direction, but still that means current is in the same direction. Then again become an electron at the end of the barrier. In a way, it didn't see the barrier. It just went through with 100% transmission. In the real space here it is drawn, it's moving with 100% transmission from one end to the other end and doesn't care for the barrier. That is the client tunneling phenomenon. Next slide. So what's good if you can just run through barriers and you are protected from all the effect of impurities and other things, nothing affects you. Only the thing which affects you is the electric field. You put large electric field, nothing else will affect you, but that electric field will drive you. Like there, you are happily running, you put more electric field. So in terms of semiconductors, they say high mobility. The transistor is having high mobility, very high velocity in response to electric field. And then I can put the field up and down, change the value, change the sign, put a sinusoidal wave in terahertz, 10 to the 12 cycles per second. Next slide. So I can, in a field effect transistor, which is component of every computer that you have today, you can put a terahertz gate here, and if there is a graphene transistor sitting here, even though it is signal is on the gate is changing 10 to the 12 times in a second, because this can respond very fast. They are not affected by other impurities and other things present. They will respond very fast, and then you can do your computation at that speed. So high speed computation is possible with this high mobility transistor, and you can compare with silicon, which has very small mobility of electron, only 400 to 1000. Graphene can have for hole and electron both almost 1 million centimeter square per volt. It can be very useful for quantum computing, but I am referring to the regular computing. This is not referring to quantum computing. Okay, thanks. So, seeing is believing. So I will show you another fascinating property of graphene, that you can see and think. See, you might say all of these things which need red blood cell and the other experiment with transistor, FET, this, you need some lab to do it. So are there any unusual phenomena of graphene which we can do without all of these things? Now this is not a do at home, but if you can get a piece of graphene, then you don't need anything more. So next slide please. So this is the idea conveyed in this picture. It's just air and one sheet of graphene, one layer, two layer are there on an opening. The opening is a transmission electron microscope grid, but for all practical purpose, just any grid. If I can take a grid and put graphene on it and just look through it with my naked eye, some light will be absorbed by the graphene. Put any material, put glass, put wood, everything absorbs some light. And how much it absorbs depends on the material. Right? We will say glass does not absorb too much visible light. But if you take some of this translucent glass, as you can see here, it's absorbing more light. And if I put some opaque object like wood, it's absorbing all the light, all the visible light. So it depends on the material. But the light absorbed by graphene does not depend on the material. In the sense, it is determined by some fundamental constants of nature. Like how much light is absorbed by one sheet of graphene is given by pi times electron charge square upon Planck's constant and speed of light. In a way, there is a fine structure constant. So just by looking at graphene and how much light is absorbed by one layer of graphene, and if one layer is difficult, you can get 30 layers or 50 layers you can make with your pencil also. Maybe you can try this experiment on a sheet of plastic. If you can get some thicker layer from the soft pencil, and if you can estimate the thickness, then every layer is absorbing equivalent to the fine structure constant. So you can add those series of absorptions. You can measure the Planck's constant or charge of electron, whatever is the unknown fundamental constant, by directly looking at graphene. So that's another unusual property. Next. I don't want to spend too much on the equation, but if I have said some unusual property, I should give some theoretical framework with minimum number of equation. And considering you are all PG physics, so I thought a little bit is okay. Now there is this quantity called Hamiltonian, and if anybody knows, very good. If I am mainly addressing people who may not know, you may think it's like energy. Hamiltonian is one way of saying energy. And what is energy? For free particle, I am sure everybody knows energy is half mv square. But momentum is P is m into v, right? P is mv. So you can also write P square by 2m for a free particle. So we say that is the Hamiltonian of free particle, P square by 2m. Next slide. And then you can add potential energy. That was kinetic energy. Then you add potential energy, whatever it can be. So that together describes the motion. If I know kinetic and potential energy, essentially I can predict the motion. That's the importance of Hamiltonian. Next one. So one of the mysteries of the 20th century is picturized here. You have the electron, and then you have these crystals. All the crystals, graphene is one crystal, anything, copper, iron, everything has some periodic arrangement of atoms, which are separated by 1 angstrom, about 1 angstrom, 1 angstrom. So people thought, why these electrons are not getting scattered every 1 angstrom? That means that current will be very low. Every angstrom there is some atom waiting, like there is a pillar every angstrom, and that will scatter. Next slide. But this is how Bloch and others managed to solve the problem. They said electron behaves in a way like it's a free particle. Energy is only kinetic energy, P square by 2m. But you need to make one change. That m you have to redefine. It's not the mass of the free electron in vacuum. It's an effective mass. That effective mass can be more, like shown here. But once you give that big effective mass, it will move in the crystal as if it's a free particle. It will respond to anything external. You put external electric field, because it is charged, the electric field will push it. But with the redefined mass in the crystal, it will move like a free particle. Next slide. And that is why we have these types of various bands. I wanted to quickly come to this picture, but without some introduction, it would have not meant something to many people. So you have this energy band. It is a parabola, and E is P square by 2m. That means it is like free particle. Where is a periodic arrangement of atoms? They are all sitting inside the M. We don't care about it now. And then there are various bands. For a metal, it's a parabolic band. For a semiconductor, you draw the valence band, conduction band. Always draw parabola, because P square by 2m, energy momentum relation is parabolic. But for graphene, it is linear. Energy and momentum sharing is mass, yes, is linear. So that means energy and momentum are proportional to each other, not squared, but directly proportional. And which other particle has that type of direct relation? Some equations are there to guide you if you not heard about this, but in case you have not heard about it, it's photons, particle of light, which are relativistic. Energy is directly proportional to momentum, and they have no mass. Photon, the particle of light, has no mass. So the electrons in graphene are behaving like relativistic, because energy and momentum are linear, not following these type of things. And they are like massless, as if they have no mass. Effective mass. Really the mass is there. You can say, what happened to the mass? Mass should be conserved. Mass is there. It's an effective mass. What is the mass when it sees the lattice? When it sees the lattice, the mass itself becomes zero. Like zero, not actually zero.
Maybe that's why we can't travel at speed of light.
And it doesn't travel at speed of light. It travels at 1/300 the speed of light, but obeys all the properties that light does. As if the speed of light itself is small. So that's a last. I will show anything more about the theoretical expressions. I want to avoid them, but maybe one Hamiltonian of the electron. It has sigma, which in your quantum mechanics course you will encounter only for spin. But this is without the spin, so it's a Pauli matrix and it's linear. And that Pauli matrix is because for the spin has this property. The spin, nobody understands what is spin. Spin of electron, people have shown, is not spinning electron. Because if it is spinning, as that book, Griffith's book also mentions, that velocity will be more than speed of light. So it's not actually rotating, but it's some kind of internal spin is there, whose origin we don't know. And that spin has this property, rather the wave function of that spin has this property that you take it around once, it won't come back, take it around 2 times, it will come back. So graphene's wave function without the spin is also having that same property which that belt was having. Take it around 2 times, it will come back. So it's called pseudo spin, false spin, but causes lot of these unusual properties of pseudo means false. Next slide. Now about that mysterious sample I told you in the beginning, as if somebody is operating the MRI machine and sees all the signals, does all the assessment of the problem, then figures out that forgot to turn on the magnetic field. Still I have diagnosed the patient, how it happened. The analogy. So let's see what happened to that mysterious sample. So what the picture was that there is some graphene here, and incidentally it's made with a scotch tape. Take piece of graphite, put some scotch tape, and then you can peel off and put some single layer graphene and then put electrodes on that. So I was telling that it was behaving like there is 6 Tesla, and I have given idea how enormous. In the rare earth magnet can only have 1 Tesla. This is much larger than that. That much field is there, but you bring a compass and it shows nothing. How that is possible? Next slide. So to understand it, a bit of physics is needed. Otherwise, at the level of phenomena, I have already explained you. So one of the things is Hall effect. Is that something you have studied in your courses? Hall effect? No. But others? Hall effect? No? Okay. Then accordingly I will give the introduction. Hall effect is very common. All the cars, there are so many Hall sensors in the cars. It's very important feature in industry today. Idea is like this: some current is passing. Then you can, if you measure the voltage like this and the current is passing, there will be some resistance, right? Resistance is V upon I. Ohm's law, right? Okay. However, I can also apply a magnetic field perpendicular. Then the electrons which are moving like this are experiencing what's called Lorentz force. V cross B, Q V cross B Lorentz force. They are deflected. It's responsible for cyclotron motion and other. Because they are deflected, the electrons start going in transverse direction. Not they were going like this, but I applied magnetic field, voltage is also there, they will deflect in the transverse direction. Then you measure the transverse voltage, that is called Hall voltage. Now why the Hall voltage does not go on building up? You are deflecting them, after some time electrons are collected here and opposite sign collected here. Less electrons, more electrons. So electric field is produced. So it will stop the process after some time, saying don't continue forever. There is an electric field, which means there is a potential. Next slide. So we speak about this transverse voltage, Hall voltage, upon the current you are passing as another type of resistance, Hall resistance. Interestingly, in many two-dimensional systems, we have quantum Hall effect. That is, this resistance is having some steps, is h upon e square into an integer. Integer can be 1, 2, 3, can also be fraction. But the basic thing is h upon e square, which has a very precise value, 25,812.80745 ohms. And you can take various samples. You make one sample of graphene, another of gallium arsenide, various other two-dimensional materials, sample 1, sample 2, everything will give only this number. So that's the beauty of quantum Hall effect. It's a resistance, transverse resistance, which is so precise, is used as a resistance standard. So in the experiment you measure two things, you pass the current, then you measure the resistance. And that resistance shows some oscillation. If you change the number of electrons, it will show oscillations like this. And it will show some step-like structure for the Hall, the transverse direction. In the same direction, it will show this kind of oscillation. In the transverse direction, it will show this type of steps. Vanishes also, yeah. Here the resistance becomes zero. Zero is exactly zero. No current is passing. Next slide. Now, don't pay attention to this. I just thought some people might be from the background who can. But the message is here, not anywhere else. The message is that, look at these stripes of the tiger. They are markers. Every tiger has unique stripes. So this signature is so unique, we cannot miss it. That's the message I am giving. And because graphene is relativistic, it is different from all other types of materials. So even the type of plateau structure and the oscillations you get are unique. By looking at the data, we can say this data has come from graphene. It cannot come from anything else. Nobody need to tell me beforehand what is the sample. So unique. So that's why like the stripes of the tiger. Next slide. Okay, I think maybe the explanation I can skip it. It's not essential. Also in the interest of time, please carry on. Next slide. Next slide. I'll skip this. Yeah. So coming to this mysterious sample, what I did is as always, I measure the sample. I sweep the number of electrons in the system at room temperature. Nothing significant happens. Resistance goes up and comes down. But when I cooled the sample, I found that it has these oscillations. These oscillations come very periodic oscillation when you have this large magnetic field. But I forgot at low temperature I was supposed to take the data without the magnetic field. So I got up to switch off the magnet. By mistake I have switched off the magnet. Middle of the night I am working alone and I forgotten to switch off the magnet. First I should take the data without the magnetic field. When I got to switch it off, I found that the field was already off and it was producing such clear signatures. Next slide. In fact, we can mark it where the position is expected. Peak 0, 1, 2, 3, 4. All the peaks are exactly at the place you are expecting them to come, provided 6 Tesla field was passing. And actually the field was not even turned on. So this was that very mysterious sample. It behaved as if magnetic field is passing through the sample. So what's the explanation of this thing which left me extremely puzzled? So what has happened? Next slide. So there was in that sample some unintentional strain. I didn't design it that way. But you can think in this picture, these are carbon atoms and these are bonds. Slightly some of them are stretched, some are compressed, and it's not in a uniform planned way, but it happens. Rarely it may happen that way. Next slide. And it becomes in the following way that strain on the sample behaves like a vector potential, which is a signature of magnetic field. Effective magnetic field, not a real magnetic field. For all practical purpose, the electron is feeling it. As if huge field, I have turned on a superconducting magnet, like MRI machine, that kind of huge field is present. The electrons are feeling it, only the electrons are feeling it, I am not feeling it. And none of the compass is feeling it. Next slide. So I made a note in my lab book, because you can't publish data which happens without your planning and you can't reproduce it, another sample, how it happened, we don't know. You can characterize nicely. So it's there in my lab book as zero field quantization. I made a note when I was doing. So others, I am not aware of anybody who found it in transport. People have done in STM and shown some Transport I am not aware other than my own work. Next slide. Yeah, so some things to remember, no basic laws of physics are violated. There is no magnetic flux through the sample, and only electrons feel that field, we don't feel it. Such things can happen. Next slide. So we thought magnetic fields are real things. You take a coil, you pass the current, you create magnetic field. But then it can be that sometimes magnetic fields, some people can feel, some people, electrons may feel, others may not feel. So what is real is something more mysterious sitting at the, it leads to the question, what is magnetic field? If it's such a real thing, why am I not feeling it? Only the electron is feeling it. Okay. Right. Next slide. And so people, as a futuristic technology, they have thought that you take a sheet of graphene and you can roll it, compress it, stretch it, produce various strain. You don't need to put anything else. You can create internal fields, internal huge magnetic field. So you can do all your electronics just by folding and cutting and doing these kind of things. It's called origami electronics. It's just an idea of the future, that devices can be made containing their own generated magnetic field. I don't have to put field from outside. No, electricity is not free. In fact, nothing should come for free. Electricity, energy has to be provided. Energy conservation cannot be violated. But many of the properties can be generated internally. We are generating magnetic field internally, but we cannot do work from there, self-created and do the work. Next slide. So this, looking at the time, I will skip some topics, but this one I will briefly mention. Very interesting mechanical properties are also there for this one-dimensional thin sheet, because we have looked at straining the sheet. Next slide. So here is a puzzle from biology. It's not yet settled to this date. I was showing you that red blood cells in our body, micrometer size cells, and they were passing through some channel. The channel I had made artificially, that was big, one cell can pass. But in our human body, there are thinner capillaries through which the cell, this red blood cell manages to pass, even though the size is very, very small, and just squeezes and then passes through. But that may not be surprising. So what? You can squeeze it and pass it through. But the problem comes here. There is a structure called cytoskeleton, which is linked up polymers which are connected with each other. Interestingly, they also form a triangular type of lattice, and that causes some kind of rigidity. So maintaining that rigidity, how you can deform this structure into another structure. So somebody has given an analogy, famous analogy. This ability of red blood cell with this rigid structure also present, and ability to pass in our human bodies through tiny capillaries, is equivalent to, anybody has a sheet of not important paper? Can I take this one? Is equivalent to, you take a sheet of paper and you can roll it into a cylinder. No big deal about that. Everybody can do it, right? Take a sheet of rectangular piece of cylinder, a sheet of paper, and roll it into a cylinder. Nothing mysterious. But now I can ask any volunteer. Is there any volunteer? Anybody? Yeah. Yes, please. Yeah. So I have made it into, please now. I have made it into a cylinder. I want you to make it into a sphere without cutting it and without stretching it. Please make it into a sphere.
I don't think that's possible.
Cutting and stretching are not allowed. Cutting, stretching, gluing are not allowed. Please make it into a sphere. Okay, very hard problem. I am sure there will be no other volunteer. Thank you. So that is the analogy of what this is able to do. It can pass through this, and the type of deformation it should undergo. Nobody understands how it can do it. Some people believe that ATP or energy is involved. Others feel that is not participating, very passive. Next slide, please. And even the mechanical property, as you see this sheet of paper, it is sagging like this. The sheet of paper just sag like this. But I can make it rigid by doing the following. Now I should fold it a little more. It's still sagging, but maybe I should practice a little more and show it. You can, if you fold more carefully a large number of times, you can make it to just stand vertical. Please try this as a homework exercise.
Hold it from the side, not like that. Just hold it down.
Yeah, this one. Yeah, this one.
No, it's not there.
Now it won't slide down. So when graphene is used like it has the same type of structure as that T-third membrane, the triangular lattice. So graphene is used to understand how this sheet can deform itself and how it can propagate through small channels. It's like a prototype to understand this problem of biomechanics. Next slide. So we can skip these things. Next slide. In fact, if you would like to have some discussions, I will also skip one more topic, or what's the plan? I think 11:30 we have to conclude with the discussions, everything. So, do you have a lot of questions or not? This one. Okay, maybe I can discuss it. I also want to keep some time so that some questions are there. Please think of any. So, okay, I will discuss this one. Graphene, a very unusual metal. Next slide. So, something very historical and important, and I don't want to give any equations here. Just think of metal. All metals. Here the list is gold, sodium, copper, aluminum, nickel, all these metals. Somebody found a very interesting way, Bloch and Bruneiser, 1933-35. They found a way that the resistance, if you scale it with some normalized, their resistance at some temperature, and the temperature on the other axis, again divided by a certain temperature of the button, called divide temperature. So scaled resistance, scaled temperature all fall on one curve. Whether it is any metal, everything falls on a single curve. As if there is some universal behavior. All of these metals, because they are all metals, they have some common property. They all behave like that. Next slide. So what's the physics behind it is conveyed through these cartoons without using any equations. At low temperature, you have an army of electrons, like here. The army is marching, applied electric field, the electrons are moving, and the resistance just saturates to some value. But when you increase the temperature, then these quantized vibrations, which I started the discussion with, they are present. Those quantized vibrations are kicking around these electrons. Just taking and throwing them here, scattering them is what we say. So that's why the resistance keeps increasing as you increase the temperature.
Graphene is
There is no graphene here, it's metals.
graphene is thin sheet of graphite, right?
Yeah,
You can call graphite as metal.
graphite is like a metal. Yeah. And it's not two-dimensional, that is one difference. So resistance keep increasing because more of the quantized vibration are present at higher temperature. The bosonic particle, look at the distribution function I have discussed. More of them are present at higher temperature. And then that causes resistance to increase because this is what they are doing. They are just kicking around the electrons. Next slide. But why graphene is different? It is a metal, but it has very few electrons. Imagine just army of 2 people. So the way they will interact with their enemies, the enemies are this quantized vibration which are throwing them left and right, will be qualitatively very different. Next slide. And then in our work we were able to show that this is not following the universal law. We are able to control how it saturates at the temperature at which it saturates can be shifted. More on details I don't wish to give. There is a new temperature regime called block tonizer regime. It's a very unusual metal. All the other metals can be explained by one, but graphene is a metal with few electrons. Because it has few electrons, every way it interacts with the outside world is different. How it interacts with the quantized vibration are different. And this is the experimental result we got, which is Professor Bhaskaran has commented other explanations also of this superconductivity or something. Next slide. Yeah, the last one, and then after that we can have some discussion. So here is a break from physics. Let's see some what is Moire pattern. Many of you may be watching football, right? Do you watch? Nobody watches football here? Anybody can raise hand who watches football? No. No. That's unusual.
You know the rules anyway.
You know the rule. So this was one famous match, Japan and Spain, which Japan won. This was played in World Cup December 2022. Japan won 2-1 with a very controversial goal. The controversial goal was whether this ball has crossed the line or not. This is the line you can see here. Just before scoring the goal, the ball is here. Should this be considered out? The goal post is here. If it crosses, it's out. But they had used this virtual assisted referee, taking the help of technology. And this is the line, this is the ball, this is out, but seen from another way, this is in. We don't know. Finally they said it's allowed. Though it looks to me it's out. And they said it's allowed and Japan won that, and that rest is history. Go on. But while people were discussing all that, and so many angles were presented in the discussion, whether the goal is there or not there, ball went out. Something interesting, people have missed that. Yeah, but our focus should not be on the ball and the goal, but on the net. If you look at the net, you can see some very different pattern. It's actually pattern produced by overlaying one honeycomb on another honeycomb. And that's how you can create new types of pattern here. There is one honeycomb, and take another honeycomb and rotate and project on top. Because the football nets are made of the same chicken wire, same shape, some reasons I can share if there is any discussion. So, football nets are made of graphene structure. And from this various angles when people are trying to understand, normally nobody will show the football played like this from the top. But for the solving that problem, whether the goal happened or not, they have to show all angles. And you can see that this type of repeating structure has formed, which is called a Moire pattern. Two of these patterns rotated with respect to each other, on one arm above the other. Next slide. So that is how different Moire patterns can form. This is one Moire pattern, but you keep rotating, another Moire pattern forms. And the repeating unit is now big unit. That is a very large hexagon, which is then repeating here. Smaller repeating units are there. Depending on the angle, it can, and it is also connected with something I will not discuss. There is a magic angle, superconductivity, At some small angle you can create superconductivity. I will not discuss that. Next. So the last thing I was going to mention is that graphene is used for in your mobile phones. Even now many of the companies have started using to reduce the heat. Apart from the electrons, this quantized atomic vibrations, the hot side has many more vibration, the cold side has less vibration. So that there is a heat current flowing and that current is carried by the vibrations. The vibrations diminish on one side, increase on the other side, level out. There is a current carried by the vibration. And to give numbers, graphene is 10 times better heat carrier than copper. And we always face this problem: overheated mobile phone, overheated laptop. Right? Thermal imaging has told that the chip temperatures can be very high. Next slide. So here I have discussed about this Moiré pattern, and for the Moiré pattern you can see that the size of the repeating unit is changing. Small unit becoming big unit. So that means that what type of vibrational modes are excited, because they depend. I was discussing the problem of the string and then we discussed graphene, is dependent on what type of repeating units are there in the system. If you change the repeating units, the modes you are exciting are different. Next slide. So this is the problem that happens again as a cartoon. Too many cooks spoil the broth. So if there are too many vibrational modes are excited because of a different repeating unit, too many phonons are there, too many heat carrier branches are there, too many phonon branches are there, then the heat soup they are unable to carry. They just keep fighting with each other. Instead of carrying the heat, they are busy scattering each other, fighting each other. Too many of them are there. Next slide. So too many vibrational modes, too many cooks, then that causes they scatter each other, they don't carry the heat, they don't do the job they are given. And the thermal conductivity, as you create these Moiré patterns, goes from very large value, like 10 times higher than copper and so on, to some very small value. We were able to measure through some experiments how this Moiré pattern can cause diminish the heat which is moving in the system by almost 10 times. And that these are very important for futuristic applications where people want to use graphene to remove heat from electronic devices. Next. So with that, I just wish you a nice adventure, because this picture is from my masters and I think most of you are from masters. So for me the adventure really started from that time, still continuing. So I wish you the same. Have a nice adventure. And thank you all for your attention. We have time for some questions. Okay. Yeah, tunneling happens to space only. You don't need any medium. You need to just bring them close enough. And in our experiments we have air, but people regular scanning tunneling microscopy machines, they use vacuum. This is vacuum between these two. Essentially there is a barrier. The electron has to leave that barrier and then come in there. On its own it can't. But
Is there any across space?
in outer space, there is so much of matter in space, there should be some electrons in outer space. Yeah, please. And then you can yeah. Any properties? Yeah, so I was giving the explanation of that phenomenon. So in the graphene sheet, when you are pulling the atoms in different direction in a non-uniform way, it is equivalent to effectively putting a magnetic field in its, because effective is important. The electrons of that graphene, as I said, their mass can change. Electron has some mass, right? What's the value? Less charge. Okay. Electron has some very small mass. Look up about that. That mass itself can also change, but it's not really changing. It's effectively changing. Similarly here, effectively magnetic field can come. It's more of a mathematical description, but it will behave as if it's really there, and but we cannot feel it. In other situations, both of us can feel it. Electron will also feel it, I will also. Both are possible. Is small compared to metal. The metal is considered an infinite reservoir of electron. Even if I remove thousands and tens of thousands of electrons from the metal, still it has not affected. But in case of graphene, that number is much smaller. Can be very, very small. Can be approaching zero also. No, there is no such thing as silly question. Anything can be asked. Please feel free. Anybody? Sorry? When? See, that jump over is a classical phenomenon. That is not surprising. If you give enough energy to the ball, there is a height, and if you give less energy, by the time it reaches the height, you give kinetic energy. It will get converted to potential energy. If increasing kinetic will reduce. But if you didn't give enough energy, you won't cross that barrier. So classically, you have to provide the energy to go above the barrier. But quantum mechanically, it's not necessary to give that. Even that will work. But it has a small chance that it will just go through the barrier. That chance is 100%. Every time it will go through whichever height of the barrier and width of the barrier, or some electrons in graphene. These are the three properties I classified. Yeah, that is interesting. Why the football net is made of the graphene-like structure, the net. So the thing is like this. Yes. So up till 1988 World Cup, the net was square. Only in the 1992 World Cup, they introduced the honeycomb net for the first time. The reason is like this: is pure money and advertising and things like that. Why? So when the ball is hitting the net, and if it is a square net, then you will see for the square net, the deformation will propagate in two directions along the two sides of the square. As the ball is going in, it will deform in one way and other way, right? But on a honeycomb, it is an isotropic 2D deformation. So that the ball will appear to just stop. You won't see any deformation on the net. The net will look like honeycomb. And there is nothing propagating like a folding or anything on the net. So when somebody scores a goal, the ball will for fraction of second appear to stop in the air, and it's just frozen in the air. It will appear like that effectively, so that the excitement will increase. When people say a goal is scored, for that fraction of a second, the excitement is more. But there is a lot of deep mechanical properties of the object sitting there. To increase that excitement, the FIFA, which is the World Cup agency, changed the square net to a honeycomb shape.
Sorry, the same question can be asked. Can be right? But also, there's nothing. What is the reason? There are two discussions. There is something called growth and thought. Very good at grasping problems. It talks about the various shapes that are in nature. Very good. You can talk about it.
Any other questions?
It's actually one of these silly questions.
Yes, yes.
Like, is there any quantum particle that can come up past light barrier and go faster than light?
Quantum particle faster than light. Yes, sir, is there anything like that? I am not aware of.
No, doesn't exist yet, but there are certain analog particles. They are taken go faster than graphene, C wave. It looks really, mathematically looks like faster than so analog particles, similarly there are so-called analog particles. You can check. So technologies can live a long way. As I said, magnetic particle does not exist in nature, but in graphene exist in the exist. Object which is relevant for some time scales and some energy scales, some spatial scales. It's not exactly true, but for practical purposes it is true.
Both are made of carbon structures. One you have honeycomb, and here you have the football-like structure. It's also called buckywall. So the arrangement of pentagons and hexagons, a mix of so many pentagons, so many hexagons in a fullerene.
You should ask him, he's an expert.
If you have no more questions, then yeah, that photon is quite a mystery. Why they exist? And the why they exist is difficult to answer for anything. Why?
We see that they exist, but why they exist, we may fact. For example, Feynman, since we are talking about says, don't ask why, shut up and tell. On the roads, it works extremely well. So there are people who are asking why it is so, why it is so, and the unending. So there are some people who work in foundations of why special here, maybe or time and so on. So they cannot stop questions like that. No, that's the classical intuition. Through mass, very number, but quantum mechanics. It's where you can have objects, or even Maxwell's theory, you have objects through mass.
There are some laws which it should obey. The existence of mass is not a law. Energy should be conserved is a law. So the laws of universe have to be upheld.